Okay. Hello, everyone. Hi. Good. Okay, so today we are going to talk about applications of what we've learned about polynomials, modulo prime, and the particular applications we'll talk about are error correcting codes. Okay, so these are incredibly useful objects, and we'll talk about two varieties of them. So in the first variety, think about the internet. Okay, so what we are doing is we are transmitting packets over the internet. Okay, and each packet has an identity. Okay, so that's the first packet, second, third, fourth, and as we send them off over the internet, when they are reassembled, each of them has header information saying which packet it was. Okay, so let's not write out the header information. Let's just write out the contents. So maybe the contents we think of them as numbers. So it's 5, 20, 1, 7. Okay, and then once you send it off, some of these packets get lost and others arrive. Okay, so maybe what you end up receiving is, well, not quite all 4 packets. Maybe the first one got lost, the second one actually arrived, the third one got lost, and the fourth one arrives. Okay, but because these packets have identity, they have header information. You know exactly that the first one and the third one got lost in transmission, and the second and fourth arrived. Now, what actually happens over the internet is, of course, as many of you might know, is that there's this protocol TCP/IP which gets invoked where you resend packets, right? So the packets that are being sent, this side says, well, okay, I'm missing this and this packet. Can you resend, etc.? And there's some rate at which the rate at which the packets are being sent get changed. But this is extremely wasteful. So in some applications, what you want to do is you don't want to do all this resending. Okay? So the question is there some way, if let's say you knew that 1 in every 3 packets gets lost, is there a way that you can reconstruct? Okay, so even though you got only 2/3 of the packets, can you figure out everything that the person on this end was trying to send you? So maybe this person wants to send these 4 packets, but instead what he does is he sends you 6 packets. Okay, is there a way of doing that so that you can reconstruct exactly what this person was sending? Okay. Okay, so that's the first problem. Is there a question? Yeah. Okay. Okay. So these are called erasure errors. Okay, and the kinds of codes that we'll use in this case are called erasure codes. Now, there's another kind of error we'll look at where instead of packets being dropped, okay, and in this case we'll think of these as not packets because we are not working over the internet. We actually think of them as characters, right? So they are characters in an alphabet, but it doesn't matter. It's sort of a similar setting. They're characters or they're numbers. It's all the same thing for us. And now instead of actually being dropped, some of these get corrupted. So maybe what you get here is, so you get back all the characters, all of them are transmitted, but so you got the first one, okay, maybe the second one got corrupted, and instead of 20, it just took on some other completely arbitrary value. Maybe it took on the value 11. Okay, and you don't know which ones got corrupted. So maybe the third one arrived okay, and perhaps even the fourth one arrived okay, but some of the characters got corrupted along the way. Now, this is a more insidious kind of error because you don't even know where it occurred. Right here, at least you know that this and this packet got dropped. Here, you don't know, when you receive these, you don't know which of them are correct and which are incorrect. And now what you want to do is, as the sender wants to send some extra information so that no matter which of these packets are corrupted, which of these characters are corrupted, the recipient can figure out what the message was. Okay, so these would be called general errors. And these would be called general error correcting codes. Okay. So before we get into this, let me just say something. This is a huge subject. Okay, so you can take entire courses in this subject. We are spending exactly one lecture in it. Okay? So why do we think we can cover anything worth talking about in one lecture when, you would really spend entire courses on this, on doing this kind of stuff? Well, why would you spend courses? Because this is incredibly important. Okay, so for the internet, erasure codes come up, for example, in terms of storing data on the cloud, right? Because when you're storing data on the cloud, you don't know whether certain nodes will fail, and you want your data to be available to you, right? You want reliability, but based on unreliable components. And so what would you do? Well, you want to distribute the data that you have on the cloud in such a way that even if some of the nodes fail, as long as you can get back some of the information, as long as, say, 50% or 2/3 of the nodes don't fail where the information is distributed, you can perfectly reconstruct whatever your files were, right? So those are the kinds of guarantees you'd want from this. And so this is why this is an extremely important thing, right? These kinds of general errors, again, they happen all the time, in terms of transmission of data, right? Or transmission of even voice signals, right? Any kind of digital signals or storage of music, So these kinds of issues come up all over the place, and there are extremely brilliant solutions to this. Now, the reason that we can say something meaningful about this in one lecture, well, there are two reasons. One is that they're extremely powerful codes that are based just on these properties of polynomials. What we've already studied. The fact that when you write a polynomial where the coefficients are being interpreted modulo prime, all x is modulo prime, the values are modulo prime. This has these two very important properties, right? A polynomial of degree d has at most d roots. If you have d plus 1, the value at d plus 1 points, you can uniquely reconstruct the polynomial of degree at most d. Right? These are the properties that we need, and based on these, there are extremely good solutions to both of these problems. Okay? So then you might ask, well, given that there are these extremely good solutions that we can cover in one lecture, why does anybody take a semester-long course on this? Right? So what else is there to talk about? Well, there's a lot more to talk about because these are extremely good solutions, but you want to come up with solutions which are even faster. And so people put in a lot of time making these solutions much faster. There are other kinds of issues that come up. So here, another issue is what's the size of your alphabet, right? So if it's the English alphabet, there'd be 26 possible letters here. Okay, here, what we'll be reconstructing is something where the size of the alphabet is large. But you also want to come up with error-correcting codes where the size of the alphabet is extremely small. Maybe you're working with a binary alphabet. And so there's, even after you learn everything you do in this lecture, there's a lot more to learn about error-correcting codes. But the point about this lecture is it's actually quite extraordinary that at this level, in a course which is in the lower division, we can tell you about these extremely important, fundamental objects. And we can tell you enough so that you see an entire picture about them. You actually see from start to finish what an erasure code looks like and what an error-correcting code looks like. Okay? So that's the interesting part. Okay, so let's go ahead and solve the first problem. So let me take an example. So let's say that what you're trying to send is exactly 2 packets. So you have 2 packets that you want to send. And let's say that you know that 1 in 3 packets gets dropped. Okay. So now, how would we deal with this? Okay, so here's an idea. Let's say packet 1 has value 5. So we plot it out like that. Packet 2 has value, no, let's not make it 20, let's just make it 8. Okay, so packet 2 has value 8. So that's packet number 1 has value 5, packet 2 has value 8. Okay. And now what we can do is we could just draw a line through this. Okay. And generate more packets which lie on the line. So for example, we could make up a packet 3 whose value is now maybe 11. Okay. So these are the 2 packets we wanted to send. This is the actual message. And this is an extra packet we added on for error correction. Okay. Now, after we send them, one of the 3 packets gets dropped. Well, if this one is dropped, it's sort of easy, right? Because the message is 5 and 8. But what happens if one of the other packets got dropped? Okay, so you got the 5, you got the 11, but this packet got dropped. Well, no sweat, right? Because these packets lay on a line. And the property of a line is, it's a linear polynomial of degree 1, right? Given any 2 points on the line, you can uniquely figure out what the line is. Right? Once you figure out what the line is, you can evaluate what it at 2 and figure out what the missing packet is. Right? So it's easy. Yeah? Okay, but now, what if you had more than 2 packets? What would you do then? Okay. So let's look at the more general situation. So suppose you were trying to send. Suppose you want to send n packets. Okay. And you know that after you send the packets, however many you send, suppose you happen to know that k of them will be dropped. Suppose you know that k packets will be dropped. Okay, so what you'd ideally want to do is, instead of, this is your message. What you want to do is, in addition to these n packets, so these are your n packets, which is the message. You also want to tack on another k packets, which is part of the error correction. Right? This is to make sure that even though packets are being erased, the person at the other end can figure out what the message was. And now the property that you want is that, okay, so of course if these k packets got dropped, everything is good. Then these n are the message, and everything is fine. But the property that we want is, no matter which k of these n plus k packets get dropped, the recipient should be able to figure out what these n packets are. Okay? Now, before you knew anything about polynomials, if somebody told you this could be done, you'd have been crazy to believe that it was possible. Right? It would have been extremely gullible to believe that, you want the values of these n packets to be transmitted. You add k more packets, and now you claim that, okay, so n could be anything, right? N might be 10, k might be 90, right? So now you're saying, well, you send 100 packets, and no matter which 90 of them are dropped, from the remaining 10, you can figure out what are the values of the first 10. Right? It sounds absolutely ridiculous, right? It's too much to expect. And yet, what we know, even if you don't know exactly how it can be done, you might suspect, given what we know about polynomials, that maybe it's possible to do this. Okay? And in fact, we'll see that it is actually possible to do this. Okay? So, just to get a sense, how many of you suspect that this can be done with polynomials? And how many of you can actually see how to do it with polynomials? Oh, good. Wow. Great. Okay, so what are we going to do? How are we going to do this with polynomials? So, see, the main observation is out here. This was the case n equal to 2, right? And the reason we chose a line is because, when you have a polynomial of degree 1, you can choose 2 points completely arbitrarily, right? 2 points are completely free. Yeah? You're free to choose them as you want. And once you've chosen those two, everything else is forced, right? So now we have n points that we want to choose in a completely arbitrary way. So what do? So what's the variable we need to change to make sure that there are n points that are free? Yeah, we have to change the degree. And we have to increase the degree to exactly n minus 1. Right? Because n points are determined, polynomial of degree n minus 1 is determined by its values at n points. And you're completely free to choose those n points as you want, and you'll always determine a unique polynomial. Right? So basically, it's the same picture. Right? What do we want? Well, we set up the values 1, 2, 3, so on up to n. We look at whatever those values are, right? It doesn't matter what they are. Right? You find the unique polynomial of degree n minus 1 that goes through these points, no matter what that looks like. Okay? And then you choose another k points. Right? So you choose another k points, which are n plus 1 up to n plus k. Okay? And you take okay, so you take these values up to n plus k, and now you transmit these n values plus these k values, right? So what you transmit is p of 1, p of 2, p of n plus 1, p of n plus k, where p is this polynomial of degree n minus 1. Okay, so what are we saying? Let me fill this in. So you have messages. Your packets are m1 through m sub n. Okay, and so you find the polynomial of degree n minus 1, such that p1 equal to m1, p2 equal to m2, pn equal to m sub n. So these are your packets that you want to send, or yeah. And then, so p is of degree at most n minus 1. Yeah, the unique polynomial of degree at most n minus 1, such that p1 equal to this, pn equal to that. And now you evaluate the polynomial at k extra points. Okay? And what you do is transmit all these n plus k values. Right? And now what we are claiming is, no matter which of these endpoints get through, doesn't matter which ones, right? Remember, a polynomial of degree n minus 1 can be reconstructed uniquely from its values at any endpoints. So it doesn't matter which k of them are dropped, the rest of them get through, the recipient can uniquely determine what the polynomial was, and once they know the polynomial, they know what the values are at those endpoints. Yeah?
Seems that the amount of packets that you're sending and that information is integral to find the polynomial. So how do you send that information in lieu of it getting dropped or something like that?
How does the recipient know how many packets you're sending and how many? That's a protocol that's set up in advance. You're sending a certain number of packets. That's your message length, and right? Okay, so let's say this is in the context of watching a movie. So you're sending lots and lots of packets over, and you set up your parameters so that they are reasonable, and then the sender uses those parameters. The recipient knows those parameters too. That's part of the protocol, and then you just split up the movie into sections of n packets, and then you keep transmitting them. Yeah.
How do you know how many packets will be dropped?
How do you know how many packets will be dropped? That's another good question. Usually, you have an estimate of the, this could be based either on an estimate for that particular network, or it could be based on something which says, well, look, I want this protocol to work as long as the percentage of packets dropped is at most this much. And once it falls below this, there are no guarantees, and, right? Yeah.
So can you guarantee that it will always, you'll always be able to find the original message?
Can you guarantee?
Absolutely 100% guarantee it, or will there always be a very slight off chance,
Well, it depends upon the model, right? So if you know that at most k packets are dropped, then you have a guarantee that you can find the original message. But on the other hand, there's never any guarantee in life, right? It could be that the entire network is down, in which case no packets get through, and then obviously there's no chance you can reconstruct the message. Yeah, in the back. Yeah. Yeah, so in this case of erasure codes, one usually thinks of these packets as being much larger rather than characters of a string, right? Usually it's in the general errors setting that one thinks of it as really individual characters. Yeah? Okay. Yes?
The polynomial we're using, should it be mod some prime?
It should be mod some prime, yes, very good point. So this polynomial, we are working modulo q. So we work mod q, where q is prime, and something else. So what is another condition we need on q? Yeah, it has to be large enough to accommodate all these values, right? So it has to be larger than n plus k, right? It has to be large enough. It also has to be large enough to accommodate all the packets, right? So, if the largest value of one of these packets is something, then the prime has to be larger than that as well, right? So you have to make sure everything fits in this framework. Yes?
From n to n plus k, are those just arbitrary values that fit the polynomial, or do they have restrictions on them, like you can't pass the x-axis?
So what kind of restrictions, sorry?
You can't pass the x-axis?
Oh, no, these are arbitrary numbers. So the question is, what about P of n plus 1 through P n plus k? Are these arbitrary, or do they have any restrictions? Well, since we are working modulo q, the only restriction is that they are between 0 and q minus 1. That's the only restriction. Right? They are whatever turned out once we use this polynomial. Yes? Why are we working mod q? Okay, so the reason here that we are working modulo Q is slightly different from the reason we work modulo Q in secret sharing. So there we work modulo Q. Actually, in your virtual lab, there's a very nice exercise that shows you why you worked modulo Q when you did secret sharing. So if you work instead of mod Q, if you just work over the reals or rationals or something, then you don't actually get random. You wouldn't end up being able to show that you get no information at all about the secret. Okay. Here the issue is slightly different. Here the issue is, well, you see, you want to reconstruct the message exactly, and so if you're working over the reals, there's always going to be an error. So now you reconstruct whatever you thought the polynomial was, but there's some error, and then did you actually reconstruct the message or not? Right. So that's why you need a digital abstraction, and the way you get that is through working mod Q. Okay, so let's actually work through an example just to make everything very concrete. Okay, so let's let Q equal to 7 because we don't want to work with anything larger than that. Okay, and let's say n equal to 3, meaning we have 3 packets, meaning the degree of our polynomial is n minus 1, which is 2. Okay. Now, let's see, how would we actually do this? So remember, the way we do this is we have our 3 packets. Each of them has a value of mod 7, so it's between 0 and 6. And then we would say the first packet has value, we'd actually say m sub 1 equal to something, m sub 2 equal to something, m sub 3 equal to something. And then based on this, we would do interpolation, and we'd figure out what's the unique degree 2 polynomial that goes through all this. And then, having done that, we'd figure out, now we'd go to 4 and 5. We'd add more packets depending upon how many we thought were going to be dropped. We'd transmit them, and then the person at the other end would reconstruct. But that's a lot of work. So since we are just doing this for illustration purpose, what I'm going to do is I'm going to cheat. And so the way I'll cheat is I'll first pick the polynomial, p of x. Okay? So I'll pick the polynomial to be what? 2x squared plus 3x plus 1. Okay? So that's my polynomial. And now I figure out what's m sub 1 equal to. Well, m sub 1 is 2 times 1 plus 3 times 1 plus 1, which is 6. M sub 2 equal to 2 times 2 squared is 2 times 4 is 8. 8 plus 6 plus 1, which is 1, right? Because 8 plus 6 is 0. So m sub 3 is what? 2 times 3 squared, 2 times 9 plus 3 times 3, 9 plus 1. So it's 3 times 9 plus 1, which is 0, isn't it? Right, remember, we are working modulo 7 in all this. Okay, so now, having cheated, now we put this behind us, and now we are doing something legitimate. So what we do is, these are the messages. Okay, we happen to want to transmit the message m1 equal to 6, m2 equal to 1, m3 equal to 0. And so what do? And we are thinking we might have k equal to 2 erasures, 2 packets being dropped. So now we are starting from scratch. So we say, okay, so these are 3 messages. So we have to figure out a polynomial of degree 2 such that p of p1 equal to, so we want to figure out p of x. We want to find p of x such that p of 1 equal to m1 equal to 6, p of 2 equal to m2 equal to 1, p of 3 equal to m3 equal to 0. And so we laboriously work our way through Lagrange interpolation, and having worked through it, we figure out that p of x equal to 2x squared plus 3x plus 1. Okay? Because that's a unique polynomial, and, we just guessed that this is the right answer. Okay, so having done all this, now we figure out what's P of 4. So 2 times 4 squared plus 3 times 4 plus 1 is, oh my God. Is it 3? Okay, 2 times, yeah, okay, so it's 4 times 4 plus 1 is 3, yeah. And P of 5 is, okay, we have, what's that? 10. Yeah? Yeah, it's 3, minus 4, right? Okay. So now what we do is we actually transmit the packets 6, 1, 0, 3, 3. Okay, so that's what we actually transmit. And then the person at the other end only receives 3 of them. So some of these are dropped along the way. Maybe it's this one and that one. And so now what they are looking for is a polynomial such that, so they say, well, find, they're in order to do the reconstruction, they're trying to find a polynomial R of x such that R of 2 equal to 1, R of 4 equal to 3, R of 5 equal to 3. Right? And so now this person does polynomial interpolation. They have the value at 3 points. It's a polynomial of degree 2. They can figure it out uniquely just by using interpolation. Okay? And so they do this, and they figure out, lo and behold, that the polynomial is exactly this one. Once they know it's this one, they substitute x equal to 1, 2, 3, and they figure out 6, 1, 0. That's the message. Yeah.
How do you know that the ones that you receive are like the second, fourth?
Oh, because remember, we are working in this setting where, it's like in packets in the internet where there's header information. So when you receive it, you know exactly which one it is. Right? Yeah.
So why did you choose Q equals 7? Is that really arbitrary?
I chose Q equal to 7 because, I was somewhat confident we could work through with do all these calculations mod 7. Right? So if I'd chosen something much larger, we'd have been in much more trouble working our way through the example. Right? But what would you do in practice? In practice, you'd want the prime to be large enough so that it was larger than n plus k. So you know how many packets you want to send, you know how many errors you expect, an upper bound on the number of errors you expect. You also know how big these packets are, so you've got to make it large, Q large enough so that it can, it's bigger than whatever number you are trying to send, right? Yeah. Yes? What does it mean to send the polynomial? You mean why not send 2, 3, 1? Right, that's what the polynomial is. You'd send these coefficients 2, 3, and 1. But now, remember, when you're sending these, some of the coefficients would get erased. And then what do you do? Right, so the whole point of this is that when you're sending information, it's not reliable. Some of your packets get dropped. And so what we're trying to do is, instead of just sending the information, we send also some redundant information from which we can reconstruct the parts that we really want. Okay? Yeah.
What would happen if you weren't working with real numbers?
Well, what would happen is, so first of all, you really can't send real numbers, right? You only send an approximation to them, right? So now, just think of that picture we had. Now, every point would be approximately where it was supposed to be on the polynomial. And then there'd always be this question, how much errors, what kind of error do you have when you reconstruct the polynomial? And therefore, how close are you to the actual message that you're trying to transmit or receive? Okay. Okay. Let's see. So shall we take a 1-minute break and then we'll go on to general errors? Okay, so let's talk about the case of general errors. So let me assume that now what I'm trying to transmit is, let's do a specific case. So let's say that n equal to 2. So we have 2 characters that we are trying to transmit, right? So we have m sub 1 equal to 2, m sub 2 equal to 4, something like that. And let's say that we are afraid that there might be one error. But unlike the previous case where the error was an erasure, now this one error could be that a character got changed into something completely different, right? So, and we didn't know which one. So let's see how to deal with this case. Okay? So again, I claim the way to think about it is just you have two characters you're trying to transmit. So, well, let's see. So the first one takes on value 2. So you plot it. Second one takes on value 4. So you plot that there. And then the most, the obvious thing to do is to draw a straight line through this. So I guess it goes something like this. And now what we'll go ahead and do is we'll just pick values 3 and 4 and go ahead and transmit these values as well. Right? So instead of sending the message 2, 4, the message we sent is 2, 4, 6, 8. So this is what we're sending. Okay? And what does the other person receive? Well, the other person receives this with one of these values changed. Okay, so maybe 4 got changed to something. So instead, what they see on that side is not 2, 4, 6, 8, but they see 2, 11, 6, 8. Something, right? Maybe not that much. Maybe the change was only slight. So, maybe it's harder to detect the error. So who knows which one is supposed to be the correct value? Okay. So now if you look at the actual received value, they look like this. So there's this one, there's that one, there's that one, there's that one. Okay? So now, can you propose an algorithm that the recipient can use to figure out what the error was and where the error was, and therefore to figure out what the correct polynomial was, and so what this message was? What would you do if you were trying to figure it out? Sorry? I'm sorry? Interpolation of what, though? See, if I interpolate these two, it depends. If I interpolate these two, I get that line. If I interpolate these two, I get this line. If I interpolate these two, I get that one. But if I interpolate these two, I get the correct one. Right? So you get correct or incorrect lines depending upon which 2 points you choose. So how do you know which one is the correct one? Yeah. So take the one which has fewest errors. So why does that work? Why is that a good idea? Yeah.
Because the one with the least errors will match all but the ones that are incorrect.
Yeah.
The correct will match fewer. It will only match with. It won't be able to match with all the ones that are correct.
Okay, here's the reasoning. The reasoning is actually equally simple, but much more sharp. So the reasoning is this. There's a line, actually the original one, on which 3 of the received points lie. Right? Why 3? Because there was only one error. We sent 4 points, there was only one error. So 3 of them lie on this line. Now look at it from the point of view of the recipient. The recipient says, here's a line, 3 points lie on this line. I don't know whether these 3 points are correct or wrong because, this person doesn't get to see what the labels are. Right? All this person knows is there are 3 points that lie on this line. Right? Okay, but now this person still reasons like this. This person says, look, there are 3 points on this line. I know that there was at most one error. Right? Which means that at least 2 of the points on this line are correct. Now, what happens as soon as you know that 2 points on this line are correct? It means it's the correct line. Right? Because as soon as you have 2 points on a line, you know it's the correct line. Because 2 points determine the line. So as soon as you found any... So the reasoning is, since we found a line with 3 points on it, we know it must be the correct line. Why? Because we don't know that all 3 points are correct, but we know that at most one of them is wrong. So 2 must be correct. Therefore, it's the correct line. Therefore, the third point is also correct. You see? That's pretty clever, isn't it? Okay? So that's the reasoning we'll use always. Okay? So not only for n equal to 2, but for any n and any k. Okay, so now let's do this again. Okay, so let's do the same reasoning again with arbitrary n arbitrary k. Right? So, okay, here goes. So now we have n packets, or n characters, m1 through m sub n. Okay, this is what we want to transmit. We have k errors. Okay? So now what do? Well, we go ahead and we plot things out, and we find a polynomial of degree n that goes through all these points. So here you have m1 sub 1, m sub 1 to n, m sub n. Okay, so we just plot out all these points. We found this polynomial. Okay, so we started with the polynomial. It started with these points. We interpolated. We got a polynomial piece p, such that p of I equal to m sub I equal to 1 to n. So it's of degree at most n minus 1. And now we do almost like we did in the erasure case, except we have to do a little bit more. So there, if we had k errors we were trying to guard against, we had to transmit k extra points. Now we are trying to guard against k errors, so we have to transmit 2k extra points. We have to transmit 2k because these are harder errors to deal with. Right? It's not just erasures, we don't even know where the locations of the errors are. Okay? But it's still remarkable that with just 2k extra points, we can still figure out what the original message was. So now we go on to n plus 1. So we go n plus 1, ... all the way to n plus 2k. Okay? So we go ahead and transmit all of these. And now what are we claiming about this? Well, what we want to claim is that if you can figure out so now what happens? Well, there are k errors, right? So some of these points just don't look like this. Instead of this, we got that. Instead of that, we got this one. So on. Instead of this, we got that one. So we got k errors. Okay? But still, if we got k errors, n minus k of these points sit on this polynomial. It's still of degree n minus 1, right? So we know there's a polynomial of degree n minus 1 such that, so there exists polynomial, actually it's the same polynomial p of x of degree n minus 1 such that n plus k of the received points sit on that polynomial. Okay. Now I claim the fact that n plus k of them sit on this polynomial means that this is the correct polynomial. Okay, so, sorry. Let me back up. So now what you do is you look for a polynomial on which as many of the received points sit as possible. Or, if you want, look for a polynomial on which n plus k of the received points sit. As soon as you find a polynomial of degree n minus 1, okay, so if you find a polynomial r of x of degree n minus 1, which is consistent with n plus k of the received points, then you can claim that r of x must be the same as p of x. How do we know? Well, because, you see, r of x is consistent with n plus k of the received points. We know there are at most k errors. So of these n plus k points that it's consistent with, there are at least n which are correct. Right? There's a unique polynomial of degree n minus 1 that goes through them. We know that the polynomial p of x goes through them. Therefore, r of x must be that same unique polynomial. So r of x must be equal to p of x. So we've reconstructed the original polynomial. And so now we can just evaluate r of x at 1, 2 through n, and we get the message. Okay? Yeah.
So in this case, how would you know that there are k errors? Because before you said, like, oh, the protocol is
Oh yeah, how would you know? How would you know how many errors there are? Well, you would assume that there are at most k errors. So you design the code so that it tolerates up to k errors, right? So maybe, so depending on the context, if it's a CD, you sort of expect that the error rate is less than 5% or whatever it is, right? And then you design your code accordingly. And then if the error rate is higher than that, maybe your protocol just doesn't work, right? But what it does is it takes it from so if you didn't have error correcting codes, you couldn't deal with any errors at all. And now what it does is now you can deal with errors up to a certain percentage. And now you just have to make sure your hardware is good enough, or your transmission lines are good enough, your signal's strong enough so that your error rate is low. Yeah? Yes?
Isn't it really hard to find this polynomial for any arbitrary input to this message, though?
Oh, yeah, very good point. So so the question is, how do we actually find this polynomial? So here, in this case, what we could have done is we had 4 points, and then we could take every pair of them and look at the line through those two and see if one of those contained 3 points, and then we'd be done, right? Here, we have n plus 2k points, and now we choose every possible n plus k of them, or n of them, do this Lagrange interpolation and see how, whether any of those polynomials is consistent with n plus k, right? But the point is, there are many, many possibilities, okay? It's really, if you want to know, it's an exponential number. So this is really not good. Okay, so even though this is a way of sending the message so that you can reconstruct the message, even though there are 2k errors, you can reconstruct the message. The algorithm that we have for reconstructing the message is not very efficient. It takes exponential time. Okay? So now for the rest of the lecture, what I want to show you is there's actually a brilliant algorithm that shows how to reconstruct this polynomial very quickly in this exact setting. Okay? So the algorithm is due to Berlekamp Welch. And Berlekamp is a professor emeritus in the math department here. So this is an extremely beautiful algorithm. It's just about easy enough that we can teach it in this class. So, which means that that's another way of saying you have to pay attention, because this is where you're being stretched to your limit. So let me just say again, you're being stretched to your limit, not in the sense that it's going to be very complicated, but in the sense that if you really want to understand it, it's somewhat it's a remarkable algorithm. There was no reason to a priori believe that there would be such an algorithm. So there's a bit of magic about it. And so I'll show you how this algorithm works. But before we start on the algorithm, let's just make sure we understand what the protocol is and what we are doing, right? So remember, what we are doing is, again, we've picked a prime, so we are always working modulo q. Q is large enough. And what did we do? Well, we had a message, a sequence of characters m1 through m sub n. Each m sub I is between 0 and q minus 1, right? And then, so when we transmit, all this information, we expect to have k errors. So we are trying to guard against those k errors, and the way we do that is we interpolate a unique polynomial of degree n minus 1, at most n minus 1. We go ahead and take this polynomial p of x, we evaluate it at n plus 1 through n plus 2k to get the redundancy, and then we transmit all these values. Some of them get corrupted. as they are by the time they're received. And then what the recipient wants to do is to find a polynomial. Okay, so the recipient doesn't get to see this polynomial. The recipient doesn't get to see all these values. Instead, the recipient gets to see this value, that, this, that, etc. Okay? And now what the recipient wants to do is figure out what the original polynomial was. So what we're claiming is, if the recipient tries all possible ways of reconstructing a polynomial, which means choose every set of every set of n points that are received, and see what's the polynomial that goes through those. Like we did here, take every pair of points and take the line through them. You get different lines. So here, take every set of n received points, find the polynomial of degree n-1 through them. You'll find different polynomials. And now see if there's a polynomial which is consistent with n plus k of the received points. And the claim is that must be the right polynomial. Right? Okay. So now what we are trying to do is reconstruct this polynomial without going through this search, this exponential search. So how do we do that? So there are two or three things that there's one thing that you have to know about before we even start talking about the polynomial, about this algorithm. And the thing is, instead of doing Lagrange interpolation, there's another way that we can figure out what the polynomial is given its value at d plus 1 points. Okay, so let's say we are trying to figure out, we have a polynomial p of x equal to a sub 2 x squared plus a sub 1 x plus a naught. Okay, that's our polynomial. We are trying to figure out what it is. But suppose we are also told that let's say p of 0 equal to 2, p of 1 equal to 1, p of 2 equal to 3. Okay, so here's another way we can figure out what p is. What we do is we write out equations. Okay, so p of 0 equal to 2, meaning a sub 2 times 0 squared plus a sub 1 times 0 plus a sub naught equal to 2. Okay. Well, these are just 0. So this says a naught equal to 2. Okay. Then p1 equal to 1. This says a sub 2 times 1 squared plus a sub 1 times 1 plus a sub naught equal to 1. So this tells us a2 plus a1 plus a naught equal to 1. Right? Another way of writing it is a2 plus a1 plus a naught equal to 1. And then the third equation tells us a sub 2 times 2 squared plus a sub 1 times 2 plus a sub naught equal to 3. So this tells us that 4 a2 plus 2 a1 plus a naught equal to 3. That told us a naught equal to 2. We are working mod 7, let's say, q equal to 7. Okay. So now we can substitute a naught equal to 2, and we get 6 here, right? If we 1 minus 2 is 6. We substitute 2 here, so we get 1. Okay, so we have these linear equations. So a naught equal to 2, a1 plus a2 equal to 6, and 4a2 plus 2a1 equal to 1. Okay, so the obvious thing to do here is multiply this first equation by 2 and subtract from the second one. So you multiply this whole thing by 2. So you get 2a2 plus 2a1 equal to 5. Right, so you get 2a2 plus 2a1 equal to 5. Now you subtract from that, and you get 2a2 equal to minus 4. Right? So a2 equal to minus 2, which is 5. And so A1 is 1, right? Okay, so the point is, you can also do polynomial interpolation just by writing out equations, right? And the point is, degree 2 means that there are exactly 3 unknowns, right? The unknowns here are the coefficients, A0, A1, A2, right? So now if you evaluate the polynomial at 3 points, so you have x equal to 0, x equal to 1, x equal to 2. The fact that this is a polynomial, you have x squared, x cubed, whatever, it doesn't matter, right? Because x, we are substituting actual values for. We have x equal to 0, x equal to 1, x equal to 2. So these get evaluated for each of these equations. And so you only have 3 unknowns, A0, A1, A2, right? As long as you have 3 equations, you'll be able to solve them, as long as the equations are not dependent. Okay, it turns out these equations will never be dependent when you're solving them for polynomials. Okay, and so then you just solve these simultaneous linear equations. You have 3 equations, 3 unknowns. You can always solve them, and that's how you figure out the values. Figure out the coefficients. So that's another way of doing interpolation. Okay, so now. Okay, so now let's get back to Berlekamp-Welsch. Let's get back to how we actually reconstruct the polynomial. Okay, so remember where we were starting from. We have our characters m1 through m sub n. This was p of 1 through p of n. And then we also transmitted 2k extra values, where k was the number of errors we expected. So we also transmitted p of n plus 1 through p of n plus 2k. Right? Okay. So these were the extra things that we added in for redundancy. Okay? All right. So now, this is what we transmitted. But what was received was something different. So the received, this was what was sent. What was actually received was R1 ... R sub n ... R sub n plus 2k. Right? That's what we actually received. And many of these received values were the same as what was sent, but k of them were different. And now, given these received values, what we are trying to do is we are trying to figure out what was the polynomial. Okay? Okay. So that's the problem that we are trying to solve. Okay, so here's what Berlekamp-Welsch tell us. Okay, that what Berlekamp-Welsch tell us is that there exists a polynomial q of x of degree I guess, am I using of degree n plus k, and a polynomial e of x of degree k, such that for I equal to 1 to n plus 2k, q of I equal to r sub I times e of I. Okay? So, and such that Q of x equal to P of x times E of x as polynomials. So there's a polynomial, so that Q of x, so E of x has degree k. We know P of x was a polynomial of degree n. This is our original polynomial up here. Okay, I'm writing it as capital P just because, just to, okay, so think of this as capital P1, capital P. Okay, so these are polynomials. So it's saying there's a polynomial Q of x of degree n plus k, and another polynomial of degree k, so that P of x is the, P of x is Q of x divided by E of x. Okay, so I can find two polynomials, one of degree n plus k, one of degree k, such that P of x happens to be the ratio of these two. Okay, not only is it the ratio of these two, but you see, the received values are not necessarily consistent with the polynomial, right? The problem with the received values is R of I is not necessarily P of I, right? But then Berlekamp-Welch is telling us, don't worry about it. Look, the received values are not necessarily equal to the transmitted values, the sent values. But we can find two other polynomials, Q of x and E of x, so that the polynomial we are looking for is really the ratio of these two polynomials, Q of x and E of x. But moreover, the received values are exactly what, they are exactly what govern the relationship between Q and E. Okay? So what's the what does this imply? Well, what it implies is that for each value of I, we can write an equation. So for each value of I, this gives us an equation which we can write, which gives us the unknowns, the coefficients of Q and the coefficients of E. Okay? But there are exactly n plus 2k received values, and that's enough to figure out the coefficients of Q and the coefficients of E. But once we figure out the coefficients of Q and E, we know the polynomials Q and the polynomial E, and so we can divide one by the other to figure out what the polynomial P is. Okay, so it's this sort of very interesting way of figuring out what's really going on. Now, if you see why this is true, that's when it becomes even more interesting. Okay, but before we see why it's true, let's just go ahead and see if we understand what is true. Okay, so what we're claiming is that Q of x is a polynomial of degree n plus k. Okay, so what is this polynomial of the form? Well, it's of the form b sub n plus k x to the n plus k plus b sub n plus k minus 1 x to the n plus k minus 1 plus dot dot plus b naught. Okay, it's some polynomial like this. Sorry. It's of degree n plus k minus 1. Okay? So it has exactly how many coefficients? It's b naught through b of n plus k minus 1. So the number of coefficients is n plus k. Okay? Now, E of x is a polynomial of degree k. And it's of the form E sub, it's not of the form E sub k x to the k. It's of the form x to the k plus E sub k minus 1 x to the k minus 1 plus dot 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 plus E naught. So this first coefficient happens to be 1. Okay? So now how many coefficients are there? So the number of coefficients is exactly k. Okay? So, yeah. Which one? This one. Well, how many? It's going from 0 to n plus k minus 1. Oh, that's the you're right. 2 minus 2. Good. Okay. Yes. Oh, did I divide? No, I wasn't dividing by n and k. I was just saying that's the degree. So I was just saying, okay, that is of degree n, that's of degree k. Actually, that's of degree n minus 1. I made a mistake there. Yeah? Okay. And so Q is of degree, it's a product, so it's n plus k minus 1. Right? P was of degree n minus 1. So, if you remember. Okay, so the total number of coefficients, total number of unknowns is n plus k plus k. It's n plus 2k. Okay. Now, every time we write out an equation, okay, so every time we write out this equation, Q of I equal to Ri times E of I, okay, what do we get? So if you write Q of I equal to R of I, okay, so Q of I equal to R sub I times E of I. This gives us a linear equation in these B sub i's and E sub i's, right? Because we get B sub n plus k minus 1 times I raised to the power of n plus k minus 1. Okay, but this is a constant. I is something we know, like 2, right? It might be, so let's write it out for I equal to 2. So let's write Q sub 2, Q of 2 equal to R sub 2 times E of 2. So we are writing 2 to the power of n plus k minus 1 plus B sub n plus k minus 2 times 2 to the n plus k minus 2. So this is a constant, right? The only unknown is this B sub n plus k minus 1, B sub n plus k minus 2, plus dot dot dot, plus B naught is equal to R sub 2. R sub 2 is a known value, right? So it's something that was received by the recipient. Okay, so this is something that the recipient can substitute in here. Times E sub 2. What's E sub 2? Well, it's 2 to the k plus E sub k minus 1 times 2 to the k minus 1 plus dot 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 plus E naught. Okay, so you get a linear equation in the B's, the E's, and that's it. Everything else is constant. Okay? So you get one such linear equation for each value of I. But how many values of I are there? So the number of equations is the number of received values. For each received value, you write one equation. But how many received values are there? There are exactly n plus 2k. So you have n plus 2k equations, n plus 2k unknowns. So you can solve them and figure out what Q of x is, because you know all the B's. You know what E of x is, because you know all the E's. And so now you divide one by the other, and you get P of x, which is the polynomial we were looking for. Okay? Okay, so now the only thing that remains is to say, why is all this true? You know, where did Berlekamp-Welch get these magical polynomials Q of x and E of x from? Okay, how could they possibly know that there are these polynomials? Okay, and this is where the brilliant idea comes in. It's an absolutely beautiful idea. It's not even that hard. It's just that it's a brilliant idea. So what they were saying was, well, look, if you look at all these received values, you know, these are the values of the polynomial, but in fact, what you actually received was something different. Maybe at some of these points you actually received different values. Okay? And so what you'd like to say is that for every I, so you want to go for I equal to 1 to n plus 2k, what you want to say, is P of I equal to R of I, R sub I. This is what you would like to say, but it's absolutely not true. This is actually false, right? This is not true. So now, what else could we say? Well, instead, what they say is, well, look, why don't we introduce a polynomial, which we'll call the error locator polynomial? Okay, so we'll let E of x be our. Okay, so let's call this the first error, okay, so let me call it F1. This one is F2. That one is F3. Okay, so you have k errors. Okay, so, and let's say the location of the errors is F1, F2, F3, up to Fk. So let's introduce the error locator polynomial, which is x minus F1 times x minus F2 times so on up to x minus Fk. Okay, we don't know what F1 through Fk is, but there's some polynomial like this, which happens to be 0 whenever we have an error. Right? Why is it 0 whenever we have an error? Because we defined it that way. Okay, so E of x is 0 whenever x is the location of an error. There are exactly k errors, and on exact all k of them, it's 0. Right? By definition. Okay? So now, instead of writing this equation, we can write a different equation, which is P of x times E of x equal to R sub x times E of x. Why is that? You see, when you have an error, if x is an error, then P of x is not equal to Rx. Right? The sent value is not equal to the received value. But E of x is 0. So both sides are multiplied by 0, so you have equality. Okay? So there are two cases. Case 1, x is an error, in which case 0 equal to 0. Both sides are 0. Case 2, x is not an error, in which case P of x equal to Rx. Okay? So regardless of whether we are in the error situation or not in the error situation, the two sides are equal. Yeah? Does everyone see that? Okay. So now, what we do is we call this polynomial Q of x. Okay? And so Q of x has degree, well, this was of degree n minus 1. This was of degree k. So this has degree n plus k minus 1. And so that's where we got this equation, Q of I equal to R sub I times E of I. Okay? That holds for all the received points. Okay? And now, most of the received points are consistent with the polynomial P of x. And that's why you can show that if you take Q of x and divide it by E of x, you actually get P of x. Okay, it's a simple exercise. Okay? Because these received points, most of them are consistent with the polynomial of degree n minus 1. And so you can show that that's the unique polynomial of degree n minus 1 that will be the ratio of Q of x and E of x. Okay, this is where the brilliant, it's sort of a very brilliant idea. It's a bit of magic that works, and it just completely takes this apart, right? Okay. Yeah. Quick question.
So you said that P of x is equal to the ratio of P of x over E of x.
Yeah.
But then what if E of x equals 0?
Yeah. Well. So what you can show is that E of x won't be 0. Right? If there are no errors, then E of x will turn out to be 1. Yeah? Okay. Yeah. Okay, so I guess that's it.